Hello, Physics 135 students, and welcome back for virtual class number 7, and a very belated welcome to week 6 of Thousand Pardons for this coming out quite a bit later than usual. The good news is that I know that a lot of you end up viewing these videos or at least completing the quizzes on Sundays. So I hope that this is not too late. If you find this burdensome in any ways with this coming out, on Saturday rather than quite a bit earlier, please just email me. I'm very happy to work with you there. As far as why this particular video has come out so late, I think you'll get a sense of why as we go through. There are a couple of reasons. One, and probably the most important one, is I really wanted this to be as good of a lecture as possible. I think that I really poured my heart and soul into creating this material and trying to make sure that there were plenty of multimodal expressions of what we'll be covering. The other reason, not maybe quite as wise on my part, is that I have two research projects that I was trying to more integrate. One, I was hoping was really a student project that I supervised over the summer. I was hoping would be published by now, or at least submitted, and it's not quite there. We had a meeting on Thursday, and he's almost done, but not quite there. And then I was hoping to make an activity out of a research project that I'm involved with exploring alternatives to general relativity. And that would have been very math heavy and or very computer sciencey heavy. So I didn't find quite the right way to approach it from a 100 level course and decided not to include it. If you find this all interesting, then please reach out to me though. Okay, so without further ado, we have an icebreaker today. So for last week's icebreaker, kind of interesting. At least a couple of you didn't have senior quotes, so maybe I've dated myself by asking about senior quotes. In this case, we're going with if you were forced to live for 3 months in a country whose native language you cannot speak, where would you choose and why? So if you're bilingual, you cannot choose, either of your native languages, etc. So pretty fun one. I haven't been on the Discord in a little while, so hopefully that even more of encourages you all to communicate with each other. I've removed the community building part because it felt like I was kind of twisting arms there, and it's totally understandable. As much as I want to try to build up a virtual community, I do understand that for a lot of you, you're on campus and maybe you do meet up with each other in person. In person is a lot easier than virtual. Okay, so for myself, well, I mean, I obviously had to do this when I was living in Germany. I did try to learn the language for, admittedly, like the first 3 months before I gave up for the subsequent almost 1 3/4 years, largely because the institute I was teaching at, or excuse me, was researching at, was in English. And then everyone I talked to ended up switching from German to English pretty quick. So it felt a little bit frustrating to try getting a practice in. But it was still fun. I still learned some German. So, but now, let's say I'm forced to live 3 months. I love Italy. I really love Italy. I spent a couple weeks there this past summer, and it is one of my favorite places in the world. All right, and so now it's your turn. Please go ahead and pause the video and address this icebreaker. It'd be great for you to still use the Discord. Again, I'm not really policing that this semester. At the very least, please do email me your answer to this icebreaker. Okay, so for today, and the other kind of reason why this presentation is delayed is because for a little while I was trying to cover everything, and I ultimately decided that let's just cover the first half in a good amount of detail because already I think that this will be the longest lecture I've probably longest single lecture I've ever created. Um, but I think a lot of it is very fun. Hopefully you all enjoy it too. There's unfortunately no worksheet, but there are quite a few attention checks to try to keep you on your toes. And I'll try to suggest breaks here and there. So today, really the big emphasis will be on general relativity. We'll be going into the solutions to general relativity, not all of them, of course, but the four main metrics, as well as the classic solar system tests of general relativity. There were three that Einstein originally proposed, and then a fourth one that didn't arise until the 1960s, but together they're still considered the four classic solar system tests. Then we'll look into somewhat more modern tests of general relativity, including the Hulse-Taylor pulsar, gravitational waves, uh, partly for purposes of time and again getting this out sooner than later. Decided to not include gravitational lensing, at the very least today. For sure, if you take Astro 100, the solar system with me, as well as to some extent Astro 5 stars and galaxies, you learn about gravitational lensing. But I have a feeling I'm going to include this later in the semester anyway. And then another actually solution to general relativity has to do with Friedman's expanding universe and Lemaitre's observations and work. So we'll talk about kind of these three key elements: the cosmological principle, Einstein's static universe, and relatedly the cosmological constant, which we will revisit much later in the course. And then we'll start to discuss the expanding universe. And then we'll have to defer to next time about the Great Debate and about Harvard's computers, or Pickering's harem, is another way to kind of phrase that, which is kind of fun. Okay, so now on to general relativity and understanding metrics. Our goals for learning. First, and importantly, kind of a definition. What is a metric? Second, I'd like you all to make sure to pay attention to the slides that follow and try to address the second attention check. What is the appropriate metric for purely spatial considerations? Third, how do the Euclidean metrics and Minkowski metrics differ? And then fourth, kind of similarly, how are the Minkowski and Schwarzschild metrics related? Fifth, how does the Schwarzschild metric suggest the existence of black holes? And then sixth, what are the four metrics of general relativity, and what assumptions do each one of these metrics make? Okay, so moving right along, in terms of a metric, this is literally a way to measure. This is in quotes, but this is my own phrasing here, or own definition. And is intimately related to the roots of the word metric. Now, in terms of the different types of metric, for the Euclidean metric, this is the distance between 2 points, and the Euclidean metric says that the distance between any 2 points, really the shortest distance between any 2 points, is a straight line. And so for computing that shortest distance between 2 points, we can express this really with the Pythagorean theorem that if we have 2 points, you can make a right triangle, and then the distance is the square root of the squares of those two other distances. So we can break down those distances into different coordinates, right? So we can have an x distance and a y distance. And then just for simplicity or cleanness, I don't have a square root here. I'm representing this still as the distance squared. But that's pretty standard or par for the course in special relativity too. So we get to keep this in a form more similar. All right, and then for special relativity, we use what is called the Minkowski metric. This is intimately related to the Lorentzian transform that you all have not learned in detail, but if you take modern physics, you certainly would. So the Minkowski metric says that, okay, we still can think of a distance between 2 points, but that distance is not really necessarily like a straight line, quote unquote, this distance depends really on the separation between those 2 points in space versus in time. So the Minkowski metric, we have this distance still d squared. Um, Notice that there is a minus sign for c squared delta t squared compared to the spatial coordinate squared. And of course, for the Euclidean metric, we could have had plus z2 minus z1 squared. And similarly, for the Minkowski metric, we can have, I've only written down one spatial dimension for simplicity, but we could write down like another subtraction for a second spatial dimension, and a third subtraction for a third spatial dimension. So you can see now that in particular, the distance would be, well, the largest value for a purely time-like uh, distance, whereas if we have a space-like distance, then looks like we have a problem, because then if we take the square root, we'd have a negative number. And that's correct. We purely spatial distances in special relativity are would be kind of imaginary because they cannot be connected um, due to the propagation of light. In other words, to go from one spatial point to another spatial point at the same time is not allowed. You'd have to travel faster than the speed of light for that to be possible. Anyway, and then really the minimum distance between 2 points. So keep in mind that space-like distances are imaginary, so they're not like physically allowed. The longest distance between 2 points occurs when we have a purely temporal line, and then we can have a zero or minimum distance between 2 points when an object travels at the speed of light, such that the spatial displacement is really like 1 light year per year. So, in other words, uh, you need the change in space to basically be, related to the speed of light. Okay. And so just reiterating and kind of some of the jargon there is that for that shortest distance in the Minkowski metric, we call that a null line. Null because, again, this distance is 0. And again, that occurs when an object moves at the speed of light. So in terms of the difference between these two metrics, really the difference is that for the Euclidean metric, you are taking the sum, or it's the Pythagorean theorem, whereas for the Minkowski metric, it is based on the Lorentz transform. So there's a subtraction between the time-like and space-like coordinates. In other words, time is a kind of special coordinate in the Minkowski metric, as well as in the rest of relativity. Okay, so moving on. Um, in terms of this Minkowski metric, so this was first identified by Hermann Minkowski a few years after Einstein published special relativity. And one of my favorite quotes, there's actually really a lot of quotes that we'll encounter in today's lecture, but one of these historic quotes I think is really, really great, where Hermann Minkowski said, as you can see on your screen, but in case it helps for some people to listen, the views of space and time which I wish to lay before you have sprung from the soil of experimental physics, and therein lies their strength. They are radical. Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. And I think that the real key part here is that this Minkowski metric, again, is rooted in the Lorentzian transform, or in other words, in the Michelson and Morley experiment and similar experiments that show that the speed of light is constant. And really, it was through this very solid experimental backing that special relativity was able to take root. And similarly, is really in rooting itself in experimental evidence that general relativity was eventually accepted. All right, moving along. So, in addition to the Minkowski metric, we have another metric, and it's going to be called the Schwarzschild metric. And actually, this was published the same year that Einstein published his theory of general relativity. This was during the years of World War I, and his uh, crazy enough worked out in the German trenches. And so Carl Schwarzschild came up with this, and unfortunately, a year later, he passed away. Not, it seems like he was not um, um, killed directly in war, but kind of one of the many, many victims of the war in terms of disease. So Carl Schwarzschild, remember this Minkowski metric is for special relativity. Carl Schwarzschild was really the first one that came up with a solution to Einstein's field equation. So in terms of what Einstein's field equation is, which is related to general relativity, let's dive into that. So very briefly, it's, I would say, a very beautiful equation. In the same way that E equals mc squared is um, absolutely simple and very cleanly expressed, Einstein's field equation can also be written in a very succinct manner. G mu nu is equal to kappa t mu nu. But okay, there's a lot of terms that we have to define here, so let's break this down. So the first term is the so-called Einstein tensor. And this basically indicates how space-time curves. And I'm going to talk about space as being kind of analogous or kind of a shorthand for space-time. But do keep in mind that just like for the Minkowski metric, we have space and time. For general relativity, all the metrics do involve space as well as time. All right, so this curvature of space-time. Now, just how space-time curves is related to T mu nu. This is the so-called stress energy tensor. And as far as like, okay, why is it stress energy? Keep in mind that in Newtonian gravity, we have maybe analogously some effect that is felt by matter traveling through space due to a mass. From special relativity, we have E equals mc squared, right? So, okay, it seems like just mass should matter. But really, this is a simplification. And truly, in special relativity, we have again some more Pythagorean-like theorem where the total energy is really the momentum of a particle combined with its rest mass. So, in other words, it's really the total mass energy of a system. And then the stress part has to do with how there are momentum terms, but there are also pressure terms that contribute to this energy. And we won't really worry about the breakdown into normal uh, stresses and shear stresses here. But if you're interested, please feel free to reach out. Okay, and then the kappa term, this is kind of analogous to Newton's universal gravitational constant. Instead, we call it Einstein's gravitational constant. And then what about these? What about some of these other Greek letters, the subscripts, mu and nu? These are a shorthand to indicate that g and t are kind of special variables called tensors. And in terms of what a tensor is, this video does a really great job of explaining what these different like indices refer to. We'll very briefly take a look at this.
This represents two of the four dimensions.
Although I'm going to mute it because in this case I don't, it's kind of a robotic voice that I don't absolutely love. Okay, so you have a potentially curved or warped space-time, and then if we proceed, they have all these arrows that are referring to the different components of just how that space-time might be worked. And then this video is showing that, okay, maybe the first index is the yellow vector, and the second index might be the red vector. And so there are different ways that you can move along a path. You can either move radially, or you can move again in an azimuthal direction. And it's showing that as you move in a so-called purely azimuthal direction, if space is warped, then you also end up moving like the direction of this vector a bit in the radial direction still. So you end up with a with an effect that is not purely conserved in a warped space-time when you're trying to just move along one coordinate axis. All right, so they've now shown those four different components, and I would recommend taking a look at this video in detail, maybe with the audio, on your own time. And if you'd like, you can even go ahead and pause this video and take a look at the slides and view this video for yourself. Okay, now unpause. So I was mentioning vectors here. We haven't actually talked about vectors, I think, in this specific class. So a vector can really be described as um, well, a magnitude and a direction. So the key part here I'll mention is that if we have a velocity, we can specify the components of that velocity in an x, y, and z component. Just like for when we're moving between 2 points in space, we can say that there's a change in space in the x component, a change in space in the y component. And we could go ahead and shorthand this vector v as being something like v mu, as being one index. And then that second index means that we have a matrix of rows and columns. Admittedly, I'm really glossing over a lot. For tensors, you can have subscripts or superscripts, and those are really derivatives. It's not just purely indices, but they indicate different properties of how this special quantity gets transformed when you're considering different coordinates. But we're going to gloss over that since this is a 100 level course. But if you're interested in learning more, please do reach out. Okay, so again, going back to this foundational equation of general relativity, Einstein's field equation, this, in other words, is indicating how mass energy, or that stress energy tensor, warps space-time. And that depends really on the properties, well, of that mass energy, but also on the properties of the space-time. This goes back and forth here, right? And to quote again one of my favorite quotes I would say of all time for general relativity, very succinctly put by John Archibald Wheeler a few years after I was born. Space-time tells matter how to move, and matter tells space-time how to curve. And we'll see some characters kind of related to John Archibald Wheeler later in this lecture that are connected through what's called or considered sort of the Holy Bible of general relativity, this book Gravitation, which is sometimes called the Big Black Book because it is a simply massive, probably like 10 freaking pound, not just paperweight, and that's paperback, right? It'd be even heavier as a hardcover. And it was out of print for a long time. And I was able to inherit mine from my mathematics professor. So thank you very much to Bill Block for, and I'd be happy to give it back if you want it at any point. Unfortunately, didn't get it signed by Kip Thorne, but maybe someday. Okay, so this is called the Big Black Book. It's also called MTW for the three authors' last names, Misner, Thorne, and Wheeler. And again, we'll come across one or two of these characters a little bit later on. Okay, so moving on now finally to the Schwarzschild metric. For the Schwarzschild metric, there are a couple of key assumptions that, if they're not met, would really raise some eyebrows as far as like why the Schwarzschild metric is invoked. Although very frequently it is the first thing that people consider with respect to general relativity, because it is the simplest, and each progressive level of sophistication makes it much more difficult to find any sort of solution or to find what one would expect for a physical scenario. All right, so the key assumptions are that we're in a region outside a spherical mass, and we physicists love our spherical cows. Maybe I'll tell that story another day. I definitely talk about in Astro 100, the solar system. but keep in mind that almost nothing is perfectly spherical, but a lot is sufficiently close, so this is okay. Second, electric charge of that mass is zero, and astrophysically, that is perfectly fine. Um, for essentially any astrophysical object, the or the equilibration time would be very, very short for Maxwellian forces to rearrange charges to bring about neutrality, given that the Coulomb force is much, much stronger than the gravitational force. So this one's okay. This one's mostly okay. Third, and most critically, arguably, for the Schwarzschild metric, is it assumes that the mass is stationary. And this is almost never true, but there are plenty of cases where the mass is spinning sufficiently slowly that it is okay, especially in the solar system. This is perfectly fine. But in more extreme environments that are very, very common, actually, this is not kosher. And then four is that I evidently changed the expression here a little bit, but don't worry about that too much. Fourth is that the cosmological constant is zero. I guess one thing I should mention, which is kind of a reframing of, okay, we're in the region outside of a spherical mass. In other words, we're in a so-called empty region of space or vacuum. If we are in a gas cloud, then also the Schwarzschild metric does not apply. All right, and then again, cosmological constant we'll revisit much, much later in this lecture. Okay, so in terms of the Schwarzschild metric, it's actually not too complicated still, thankfully. We have some terms that are very similar to the Minkowski metric, but we have two coefficients. And notice that the coefficient for the time-like distance is is linear, whereas we have an power to the -1 for the space-like coordinate. And the spatial coordinate we're doing in radial, we're doing radially rather than in Cartesian this time, because that makes the math a lot simpler. Okay, so we have this RS. We have a radial coordinate, that's fine, but what is this RS? This RS is the so-called Schwarzschild radius. It's also referred to as the event horizon, and it, in short, refers to the region of space where even light itself cannot escape, a so-called black hole. So because this is an inverse, you can see that there are two singularities for the Schwarzschild metric. We could have R equal to RS. Excuse me, if we have, yeah, over here, rather, we could have R equal to RS, and then we have 1 minus 1, which is 0. But really, this is to the -1 power. So we really have 1 over 0. It turns out that when the radius is equal to RS, this is a so-called coordinate singularity. Remember that we're doing this in radial coordinates. If we switch to a different, like cleverly chosen coordinate system, then we don't end up with this singularity. However, it has been found, or at least to the best of our knowledge, that this other singularity, where r equals 0, is a physical singularity. In other words, we cannot change our coordinates and get rid of this division by r. Now, even though this rs is a coordinate singularity, it is nevertheless important. Again, in terms of this interpretation of where light itself cannot escape. And the mathematics behind this is really quite simple. We could derive this from conservation of energy, where we relate the kinetic energy of a photon to the potential energy of a massive object. And just like for finding the escape velocity or orbital velocity, really the escape velocity, I should say, we would end up finding that, okay, we have the radius is equal to this 2gm over c squared. So this c squared is the speed of light squared, of course, and for the Schwarzschild radius. And this has been known, or this was known, for decades prior to Einstein's field equations. again, you can do this very simply with conservation of energy, assuming Newtonian gravity. So these so-called black holes, or at that time they were referred to as dark stars, were first pointed out by John Mitchell in 1783, pardon me, and subsequently by Laplace at about the same time, really, I should say. So these have been known for, a long, long time, more than 100 years prior to the establishment of general relativity, or even some of the foundational experiments underlying special relativity. Okay, so four metrics of general relativity. We have the Schwarzschild metric, we have the Kerr metric, which has the same key assumptions as the Schwarzschild metric, but for the Kerr metric, very crucially, we do allow the spherical mass to spin. And so the Kerr metric is one of the most useful metrics. I mean, again, for the Schwarzschild metric, if we're in a weak spin regime, it can be okay. But the Kerr metric is really required for a lot of strong tests of general relativity and is ultimately what we think essentially all of reality should boil down to. And then for the Reasoner-Nordstrom metric, we have, again, the same assumptions as the Schwarzschild metric. But in this case, we allow for that spherical mass to have an electric charge. So this metric is, to some extent, pointless. It's not fully pointless, right? Because we could consider maybe some really high precision tests terrestrially, or in certain cases of exotic um, dark matter, or etc., or exotic laws of physics, maybe this could play a role. But in most astrophysical systems, again, we expect no charge, so we don't really expect the Reasoner-Nordstrom metric to play a role. And then fourth, we have the Kerr-Newman metric, which could be framed as having the exact same assumptions as the Reasoner-Nordstrom metric, but we allow for the spherical mass to spin, which again would be important, but except for that, we don't necessarily care that the mass is allowed to have a charge. And a different way of framing the Kerr-Newman metric is that we actually have the same assumptions as the Kerr metric, but in addition to the Kerr metric, where the mass is allowed to spin, we also allow the mass to have an electric charge. So in other words, this Kerr-Newman metric is the most general of the general relativity metrics. But this, as well as the Reasoner-Nordstrom, are fairly rarely discussed. And for this class, we'll by and large focus on the Schwarzschild and Kerr metric. And then again, this student's paper has not been completed quite yet. But I just wanted to give a shout out to Leon for doing a ton of great work since the summer. Leon is actually a high school student that I've been working with. And this ended up being more of a review article, although Leon learned a ton about general relativity, and who knows, maybe he'll find a new exact solution to Einstein's field equations, whether that's a metric or something rather admittedly more complicated. Maybe you'll find that out during college. Just like you all have this opportunity to do a semester-long research project, although you might want to more do a 2-year-long research project if you want to do something like this for general relativity. The tests are a little bit more bite-sized, chewable, although even then, again, I didn't quite finish that demo. Even then, it's not at all trivial. Okay, so in terms of breaking down these metrics, I did find a video that I thought was quite
Most
helpful
people know
here.
the Schwarzschild radius in the context of black holes.
And then in this case, we're going to really focus on like the Schwarzschild and Kerr metrics. I'm going to play this video at 2 times speed so we don't. So hopefully that's okay. If you don't like that, you can skip over me showing this video and check it out on your own at 1 time speed. So okay, let's go ahead and listen in.
There are many ways to define what the Schwarzschild radius is, but I think the easiest way is as follows. We could say that the radius at which a mass has an escape velocity equal to the speed of light is called the Schwarzschild radius, and any object smaller than Schwarzschild radius is a black hole. This is because we will need something to travel faster than light in order to escape it, making it invisible, hence the black in black hole. We can calculate the Schwarzschild radius of any object, and once we get that object to have a radius smaller than that of the Schwarzschild radius, it becomes a black hole. The source field radius is exactly the same as the gravitational radius, just a different name describing the same thing. For a more technical definition, the source field radius or the gravitational radius is a physical parameter in the Schwarzschild solution to Einstein's field equations that correspond to the radius defining the event horizon of a black hole. The event horizon is just the boundary where the velocity needed to escape the black hole exceeds the speed of light. So that's the point of no return that you hear people talk about with black holes. Once you get past that, even if you're a beam of photons traveling at the speed of light, you can never get back out. As I mentioned a short while ago, the source field radius is a characteristic radius for any object with mass. So basically anything except a photon and maybe some neutrinos. But for anything less than the most massive stars, this radius is going to be very tiny. You can actually calculate your own source field radius using the source field radius equation, and you can see how small you have to be to become a black hole. Something that
All right, so I love that part of the video. And then let's go ahead and move on. One thing I want to rewind to really quickly, if I can find that really nice illustration included, is that you can see that there's this kind of special red region here. So that's the Schwarzschild radius or event horizon related to the Schwarzschild radius, but not quite equal to it for definitely for a Schwarzschild metric, is the so-called innermost stable circular orbit. In other words, if you're considering matter spiraling around a black hole, there is a innermost orbit where a photon can be stable before, if it loses a little bit of energy, it'll end up falling in and not be able to escape. Okay, and then let's go ahead and move on now to the Kerr metric.
So we have the Kerr metric, which is a generalization to the rotating Schwarzschild metric, meaning it still has no charge, now it just rotates. It's got angular momentum. The Kerr metric is an exact solution of the Einstein field equations of general relativity. However, these equations are highly nonlinear, which makes exact solutions very difficult to find. Then we have a metric for a charged rotating black hole known as the Kerr-Newman metric. This was discovered shortly after the Kerr metric. And one thing you'll find which is quite common in physics or mathematical physics in general is that generalizations always come later. You have a specific use case of an equation, such as the Schwarzschild solution, and then later on you build on top of that to allow for more and more cases. So the Schwarzschild metric applies to one case, and then you have the Kerr metric, which applies to a few more cases, and you have the Kerr-Newman metric. And the same thing happened with relativity. Special relativity came first, where gravity wasn't included, for example, and then later on you have general relativity, where you have more cases, where gravity is one of those additions. Going from a special case to a general case is quite a tricky process. That's why it took decades to go from the Schwarzschild metric to the Kerr metric, and why it took many years to go from special relativity to general relativity. But as always, these things are born out of necessity. So
All right, so that's a very good point. So again, the Schwarzschild metric was derived the same year as general relativity. The Kerr metric didn't come along until the 1960s. And I'm actually not sure about the timeline for the Reasoner, Nordstrom, and Kerr Newman metric. I was tempted to say that these came out in like the 90s or so, or much, much later. But I guess Kerr was probably alive still for the Kerr Newman metric. So, I mean, possible, but not absolutely clear. Okay, so hopefully you've addressed all the attention checks 1 through 6. If you haven't, you might need to rewind the video or check out the preceding slides. And I would recommend taking a little break, standing up and stretching, because we've completed 1/3 of this lecture, and or maybe closer to a half, honestly. But upcoming, we have another major part and a very fun part. I think even more enjoyable for me at the least, compared to the metrics, are these tests of general relativity. Okay, so go ahead and pause the video and take your break. Okay, so unpause. And hopefully you did take a little break. It is very useful to take like 5-minute breaks to give your brain some ability to absorb the additional information that we're about to cover. So our goals for learning for these tests of general relativity, so you have some additional attention checks here. And oops, I thought that I had those broken down one per slide, but I guess that's fine. Attention check number 7. What are the 4 classic solar system tests of general relativity? Attention check number 8. What affected gravity probe B in its 2011 test? What effect did gravity probe B test in 2011, let's put it, and which metric was used for predicting that effect? Attention check number 9. How is the Hulse-Taylor pulsar used to test general relativity? And attention check number 10. What effect of general relativity does LIGO, Virgo, or CAGRA measure? And then even like a secret attention check, if you will. There is going to be a test of general relativity that I haven't kind of outlined here. Oh, no, actually I do, with attention check number 8. So apologies. So never mind, no hidden attention check, which is probably for the best. All right, so let's proceed with the 4 classic solar system tests of general relativity. The very first one was really arguably the experimental evidence that led to general relativity. And that was the so-called perihelion precession of Mercury. And I think it's absolutely interesting how important a role our solar system has played in the development of science. Again, it was 8 arc minutes of Mercury's retrograde motion that led Kepler to realize that the planet's motions would be ellipses. Also, if our planets did have perfectly circular orbits, there wouldn't really have been any obvious need to switch from a Ptolemaic view to the Copernican view. Anyway, so for Mercury, it had a kind of funny motion to it. Let's better understand first what is precession, though. So in terms of precession, this has to do with a change in the spin axis with time, and in terms of conservation of angular momentum, in order for that spin axis to change, that means there has to be some sort of external force. And in our cases, that'll usually be gravity. So to point this out in a little bit more graphically, this might also be dating myself, and that's a little bit strange, but ideally we'll be able to see some Beyblades here. So this is something that I grew up with. Me and my sister played with our Beyblades, but otherwise, if you've ever seen like dreidels, around the holidays or other spinning tops, then you should have some idea, but let's just go ahead and take a look at this video. All right, and so you can see that initially the spin axis, it's like this top is spinning very quickly, but it's kind of pointing in the same direction. But very quickly with time, where that spin is pointing is changing. In this case, that change is not really due to gravity as much as it's due to friction. All right, and then now they're going to battle, and evidently the white one won. And I admittedly don't recognize either of these two, so I guess this is a much newer generation than Hopper, which was, I think, the second generation Beyblade that me and my sister largely played with. Okay, so that's one example. And then just to make this a little bit more clear, we have, again, so if we have a spinning top, which is very exaggerated here, then it points, its spin axis points in a particular direction. And that spin axis will rotate basically around a circle when it's subject to a force. And so this is really like sped up compared to what the Earth's so again, Earth points to the North Star. This is something you'd learn a little bit more about in stars and galaxies or the solar system. And the sun pointing towards the North Star, that is kind of a happenstance, and that'll actually change with time due to precession. Okay, and then moving on. So in terms of the precession, of Mercury's perihelion, in other words, the closest distance to the sun, this was first realized as being anomalous, or in other words, weird, by Urbain Le Verrier in 1859. And I think it's kind of incredible in the same way that it took hundreds, if not really like 1,000 years, for the chinks in the armor of the Ptolemaic model to start to really rust, or for light to shine through them. It took hundreds of years of measurements to find a chink in the armor of Newtonian gravity. In fact, it was 150 years, not of Mercury like observations, but specifically Mercury transit observations. So these only occur when basically Mercury eclipses the sun. You never end up with a total eclipse when Mercury passes in front of the sun, because Mercury is a little tiny thing compared to the sun, and the distances don't quite work out, of course, is the other reason there. But so after 150 years, Urbain Le Verrier measured, well, so of course, Urbain Le Verrier was not involved with all 150 years of measurements, but was involved with some, and took this composite record and found that Mercury precesses 574 arc seconds per century. Again, remember that Kepler found an 8 arc minute discrepancy in Mercury's retrograde motion, and he trusted that Tycho's measurements were accurate down to 1 arc minute. And in 1 degree, remember there's 360 degrees in a circle, there are 60 arc minutes in 1 degree. There are 60 arc seconds per arc minute. In other words, a single arc second is 1/3600ths of a circle. So an arc second is very small. 574 arc seconds is a little bit larger, or excuse me. So there are 3,600 arc seconds in 1 degree, not in a full circle. 3,600 arc seconds in simply 1/360th still of a circle. Okay, so we have 574 arc seconds per century measured, which differed from Newtonian gravity, which predicted 531 arc seconds per century. And it was due to those 43 arc seconds per century discrepancy that Einstein was able to have some immediate justification or validation of general relativity. Admittedly, this was a post-diction, right? So Einstein came out with general relativity decades after this discrepancy was found, but it was a very natural result of Einstein's calculations. And then I've mentioned a couple of times for Kepler with eclipses, this 8 arc minute discrepancy in Mercury's retrograde motion. So in terms of, oh, whoops, this is wrong. That is Mars's retrograde motion, not Mercury's retrograde motion for Kepler. All right, and then back to the slides and in fact to this video. So for Mercury's perihelion precession, in terms of what this looks like, the idea is actually continuous, but it would take a kind of long time to draw all these out. So instead, let's just kind of zoom forward in time. So each orbit is drawn every 378 Earth centuries. So in other words, this is a really minuscule effect, right? But if we were to wait 3,780 years, or excuse me, no, 37,800 years, we'd go from that first orbit to the second orbit, and from the second orbit to the third orbit. So 37,800 years. It's a really small effect, in other words. And it's almost, I'd say, incredible to me that we were able to make, such high precision measurements, not just in 1859, keep in mind, but dating back to the early 1700s. All right. So ultimately, Einstein was able to show that general relativity explained that 43 arcsecond per century discrepancy. Um, but that wasn't really good enough for anyone, since, of course, everyone knew about Mercury's perihelion precession. What really launched Einstein into celebrity stardom was this second test of general relativity, of the deflection of light by the sun. In particular, for Newtonian gravity, there's a prediction that for the maximum effect, one would expect about 0.87 arc seconds for light to be deflected by the sun, whereas for Einstein, it is exactly 2 times that value. And it is, really mathematically exactly 2 times the difference. And I have 2 videos that I want to show you. This first one is really absolutely fantastic in its storytelling. So we're still going to be 2 times speed, but I want to take a look at, it's only still going to be a few minutes at 2 times speed. I want us to revel in a lot of this. I don't know if some of this is kind of mocked up to look historical versus actual historical footage, but let's take a look at all of this.
One way to see the stars while the sun is out, and that's during a total solar eclipse. You have to be at the
All right, so one little thing to mention, notice that there's not totality quite yet. You can see that the sun is bright. So that is why people a second ago were watching with their eclipse glasses.
You have to be at the right place at the right time under a clear.
All right, so keep in mind that when you have an actual totality, you do not need eclipse glasses. In fact, if you're wearing so-called eclipse glasses during totality, you're missing on the best part of the experience. You do have to be a bit careful because you need to know the timing. If in contrast to usually, usually if you try to look up at the sun, it's so freaking bright, your body will protect itself. Same thing if you accidentally touch a hot like stove, your hand immediately, reflexes back. Same thing if you accidentally look at the sun, you will reflexively look away or close your eyes, etc. Um, Problem during total solar eclipses is that just before and just after, there is potentially enough UV photons that they could cause some damage. I'm not a medical doctor, but this is what I've heard. But the overall visible light intensity is low enough that you don't get that signal to look away. So you do have to be careful about the timing to some extent. But again, if you look at the eclipse during totality with eclipse glasses, then you miss
Sky.
like this solar corona, and you'd not be able to see the stars and everything that these astronomers ended up looking at. All right, so let's a little bit less. I'll interrupt it a little bit, but I'll try to let this play through a bit more now.
Standing somewhere along the narrow path where the moon aligns perfectly between the sun and the earth. When the moon passes in front of the sun's disk, it darkens the sky just enough for distant stars to become visible. There have been many photos of total solar eclipses, but this one is special. It helped prove a radical idea that redefined gravity and turned Albert Einstein into a celebrity. Because the stars in this photo aren't where they're supposed to be. Isaac Newton laid the foundation for understanding the physical universe in the Principia, published in 1687. In it, he defined gravity as a force of attraction that draws massive objects like stars and planets toward each other and keeps them in orbit. And for more than 200 years, gravity was defined this way, as an attracting force. But Albert Einstein saw gravity as something completely different. According to his theory of general relativity, which he published in 1915, gravity isn't a force between objects in space. It's the influence of objects on the shape of space itself. According to Einstein, massive objects like the sun.
All right, so again, this kind of goes back to Archibald Wheeler's quote, who pointed this out much, much later than when Einstein's theory of general relativity came out. But Einstein did have this geometric picture at play. Again, so space-time gets warped by matter, but also equivalently, you could say that space-time tells matter how to move in terms of, again, how the planets move.
And the space around them. So when a smaller object moves in a straight line along this space, it gets diverted because of the curve caused by the mass of the larger object. That puts one object in orbit around the other. And if Einstein was right, then the same curve would divert the path of light as well. Meaning, if you observe distant stars through a telescope on Earth while the sun is in front of them, their light, deflected by the sun's gravity, would make them appear slightly out of position. It was a revolutionary idea, but there was a big conflict keeping Einstein from testing it. The world was at war. Einstein lived in Germany at the time, but his work landed in the hands of a British astrophysicist, Arthur Eddington. Even though they were on opposing sides of the war, Eddington, along with astronomer Frank Dyson, set out to test the theory. They would photograph a total solar eclipse. They needed to compare the position of a cluster of stars in the night sky with a photograph of the same stars during an eclipse. If the stars' apparent positions had shifted, it would prove that starlight was traveling through space curved by the sun's gravity. The May 1919 eclipse was the ideal one for this experiment. The sun would be in front of a very dense cluster of stars, the Hyades, and that meant multiple bright stars would be visible during the eclipse. Planning began in 1917, and a couple of years later, two expeditions departed England. One, led by Eddington, went to the island of Principe in West Africa, and the other headed to Sobral, Brazil. Two locations that were in the path of the eclipse and had favorable climates. Each group traveled with powerful photographic telescopes that could record detailed photos of space on the glass plates. Photographing the eclipse that May required transporting and then
Okay, so probably you all will not be able to export such heavy scientific equipment. The good news is that rather than photographic plates, we have digital cameras, and the equipment could be a lot smaller. I did want to mention that in terms of eclipse expeditions, although there's rather less scientific interest these days in terms of general relativity, they are still I can wax philosophic or wax poetic for a long, long time on total solar eclipses. The most beautiful natural phenomena I've ever seen. I was fortunate enough to witness the 2017 total solar eclipse in Idaho and the 2024 eclipse in Indiana. The next total solar eclipse in the US won't be until 2044 or so. It's only going to cut through North Dakota, South Dakota, and I believe Wyoming. The next great American eclipse isn't until, I believe, 2049. Now, the longest total solar eclipse of the century is coming up, though. The longest total solar eclipse of the century will be visible from Luxor, Egypt, in, I believe it's August 10th or August 12th of 2027. So I'm currently saving up. I'm going to try to book tickets or anything that I can about a year in advance. And that's definitely not a minor lift. But again, the total solar eclipse in Luxor, Egypt in 2027, it will be almost 2 times longer than the total solar eclipse from 2024 and almost 5 times longer, I think, than the total solar eclipse of 2017. So you could wait until, what is it, 2045 or 2049 for the third Great American Eclipse, which will also be the last Great American Eclipse of the 21st century. But I just wanted to point this out. I've maybe mentioned it a few times. And then, okay, I think that we've maybe covered enough here. Let's just jump into more. Well, I don't know. I do enjoy some of the historical parts. Maybe I shouldn't rob you all of that. So we have our path of totality or photographic plates. I'll try to shut up for the next minute and a half to just finish off this video.
And had favorable climates. Each group traveled with powerful photographic telescopes that could record detailed photos of space onto glass plates. Photographing the eclipse that May required transporting and then carefully assembling them in the field, with the plates tilted 45 degrees on one of the telescopes to include as many bright stars as possible. And this was the result. This is one of the few successful plates from the 1919 expeditions. It came from Brazil. It shows the eclipse during totality, the sun's corona bursting forth, and the rarely seen solar prominence.
I guess I'll just mention that this was it didn't look exactly like this. This was digitized by the Heidelberg, I think, Foundation or Heidelberg Institute. So they had something that looked they didn't have as clear that solar prominence in the original photographic plate.
Most importantly, bright stars of the Hyades. Back in England, Eddington
This part they did have though.
compared the position of the stars from the eclipse plate with another of the night sky, using a machine that can take measurements within photos at the microscopic level. The comparison revealed that the stars had shifted during the eclipse by roughly the amount that Einstein predicted. According to Newton's calculations, starlight should bend near the sun too, but if Einstein was right, that deviation would be twice what Newton predicted. Eddington's result showed that the deflection of the stars came closer to Einstein's calculation than Newton's. It wasn't a perfect match, but it was close enough to validate the theory of general relativity and completely shift our understanding of the universe. The success of the experiment was first announced in the Times of London on November 7, 1919, almost a year to the day after the end of World War I. An Englishman had gone to great lengths to prove the ideas of a German, and the news that space is warped by the planets and stars excited the world. Einstein, who before this moment was only known in the physics world, essentially became a celebrity overnight. He remained an international pop culture icon for the rest of his life, and a favorite subject of press photographers. Observing eclipses continued to be one way of testing general relativity for decades to come, with more sophisticated equipment.
All right, so we'll go ahead and end this here. I do have another video actually that I want to share with you. But yeah, definitely I'd say fantastic in terms of the historical setting to think that in the midst of World War One, there was this international, nevertheless symbiosis between, again, the theory of a German and the observational expedition of an Englishman. And hopefully in today's world we can, there's a lot of scientific international collaboration, but hopefully science can bring us together more rather than rip us apart. Okay, and then this video I think does a bit of a better job. It's not as really like visually stunning, but I would say it does a better job of really explaining this actual deflection of light by the sun.
One of Newton's laws of motion states that an object in motion remains in motion at a constant speed in a straight line unless acted on by a force.
So again, we've learned about this before. Galileo first kind of pointed out this principle of inertia, which, and then again, this is Newton's first law of motion.
In this view, gravity is a force. It can act on light and divert it from its usual straight line motion. Einstein, on the other hand, had massive objects curving the space around them. An object in motion traveling through this curved space follows geodesics, the shortest path between 2 points, unless acted on by a force. It's important to remember that in general relativity, gravity is not a force, but light will bend. Both theories have light bending when traveling near a massive object. The larger the mass of the object, the larger the bending, and the closer to the center of the object, the larger the bending. But the two theories predict different amounts of bending for the same mass and distance measurements. For light passing near the surface of the sun, Newton's theory predicts a deflection angle of 0.87 arc seconds. Einstein's theory predicts a deflection angle of 1.74 arc seconds, twice.
So one thing to point out is that, this is if the light is grazing the solar limb. And in reality, like for those photographic plates, that isn't the case, right? We have the stars are going to not pass quite so close to the sun. For one thing, the solar corona can cause a lot of issues, but this video will point that out as far as how we've been able to more recently do really high precision measurements at larger distances from the sun where the solar corona doesn't matter.
Newton's prediction. Einstein pointed out that the best way to test his theory was to study apparent star locations during a total eclipse of the sun. In 1919, a solar eclipse was slated to occur with the sun silhouetted against the Hyades star cluster, the nearest open cluster to our solar system. The British astrophysicist Arthur Eddington took up positions off the coast of Africa and Brazil, and simultaneously measured the cluster's light as it brushed past the sun. The images were then superimposed on top of an image taken at night earlier in the year. When the eclipse and night images were compared, a gap was found, and when the gap was measured, it confirmed that Einstein's prediction was correct. Here's an enhanced picture produced 100 years later by the Heidelberg Digitized Astronomical Plates Project and released by the European Southern Observatory. They scanned one of Eddington's photographic glass plates and applied modern image processing techniques like noise reduction. This version identifies some of the stars used in Eddington's analysis. But the sun's corona is strong. It interferes with all the measurements. It is estimated that errors as large as 20% are inherent in Eddington's and other visible starlight bending experiments around the Sun, but other tests have produced much more accurate results. For example, the European Space Agency's Hipparcos satellite from 1989 to 93, designed to measure parallax distances to 100,000 stars, charted the positions of stars so accurately that no eclipse was needed to see the effect of the Sun's gravity. They produced numbers with only a 0.1% error. In 2003, using radio frequency light and measuring techniques that eliminated the error-producing impact of the Sun's corona, astronomers measured how much waves sent from the Earth to the Cassini satellite and back again were deflected by the Sun. Their error rates were around 0.03%. These and many other light.
That's technically a different test in terms of the radar ranging there, which we'll get to a little bit later, although the deflection is part of it. Okay, fantastic. So we've talked about now the second test of general relativity, the deflection of light by the sun. And then let's move on. The third test of general relativity is now, I would say, a much stronger test in the sense that in both of these cases, the Newtonian theory predicted some effect. And then, especially for the deflection of light by the sun, one might wonder if there might not have been some bias by Eddington towards Einstein or so. This gravitational redshift of light, there is a prediction of zero effect in Newtonian gravity. So the fact that there is any gravitational redshift of light is very strong evidence, I would say, for general relativity being the more true, or the theory with more explanatory power, I should say, in our parlance. All right, so in terms of understanding this gravitational redshift of light, let's go ahead and start with conservation of energy. So the initial energy has to be equal to the final energy. And let's say that for our initial energy, we have some photon energy plus a gravitational potential. And then let's say that for the final energy, this photon has quote unquote escaped. In other words, it's gone infinitely far away, quote unquote, from a point mass, so that it just has the photon energy now. Really, it should be E photon 1 and E photon 2, as we'll show that this had to have changed. And in particular, this has to have changed in a certain way because this gravitational potential energy is considered negative. Again, as potential energy. And since that's the case, that implies that the photon energy must decrease as as this gravitational potential energy, which is negative, gets replaced with a zero for, again, E1 to equal E2. For that photon energy to decrease, okay, if a photon is a particle, then we could say that the speed is decreasing for the photon energy to decrease. But no, the speed of light is constant, and kind of a bizarre part of quantum theory is not just that the photon can be treated as a particle, but also the photon can be treated as a wave. So the photon's speed is constant, and therefore we don't just have to stick with the particle view where we just have kinetic energy, but we can think of the wave energy associated with a photon. So this is h times nu, in other words, Planck's constant, 6.626 times 10 to the minus 34 joules times seconds. And then we have the frequency. So overall, we have, again, a unit of energy, or joules, in the values that I quoted. Okay, so in other words, this frequency must be getting smaller, or in terms of the wavelength, then the wavelength must be getting longer. So this is a so-called gravitational redshift then, because if the wavelength starts out blue, as the wavelength gets longer, it becomes more progressively red. And again, this is not at all predicted for Newtonian gravity. For Einstein's theory, it's a really minuscule effect for the Earth, as well as for the sun. And Einstein originally suggested that, okay, it's going to be impossible to find this effect on the Earth, or really kind of in the solar system very easily. So instead, maybe can take a look at white dwarf spectral lines, since in contrast to the sun, white dwarf is much more compact and therefore has a much stronger surface gravity. So there's a stronger effect. And in fact, the first conclusive evidence for this, there was a measurement in 1925 that was later put into doubt whether they actually measured gravitational redshift as compared to some other instrumental noise or other noise effects. Okay, in terms of what this redshift is, in terms of spectral lines, if we know what a object looks like in a laboratory, say like hydrogen, like essentially all space is made of, which we'll learn about later actually. If we know that materials are made of hydrogen, we know the wavelengths or the frequencies of their lines. Redshifted means that they're shifted well towards the red, whereas blue shifted would mean shifted towards the blue. So again, this was attempted in 1925 for a white dwarf, but then conclusively measured in 1954 as an effect of 21 kilometers per second for this white dwarf Eridani B. But still, one might wonder, okay, this is not really a solar system test, or like what's going on here? And how do we know that there's not just something astrophysically weird about this system? There is somewhat stronger evidence for general relativity and the gravitational redshift of light put forth with an actual solar system test, or really a tabletop test, similar to how the Michelson-Morley experiment was done in a lab. The Pound-Rebka experiment of 1959, which was then published in 1960, was a high precision test. And we'll take a look at this diagram on Wikipedia, and all credit due to this particular Wikipedia user. So you can see that there's a somewhat sophisticated system. The main element here is that there is a vertical distance. And that vertical distance means that as this object is moving higher and lower, we have helium and then iron here. As an object is moving higher and lower, it should gain and lose energy and therefore shift its frequency. Again, depending on whether it's moving up versus down in this gravitational potential. And this was measured, again, to very high precision using a somewhat sophisticated experimental apparatus. Um, so this is something that, I mean, it would be cool if you all could do, but I think that this would be, again, beyond the scope of a sensible experimental semester-long research project. Okay, so we have our, and then in terms of moving on to higher precision, in 1976, Gravity Probe A used a hydrogen maser. And so in other words, this is like a laser. Laser is for visible light. A maser is for microwaves. And Gravity Probe A was able to detect this gravitational redshift of light down to 0.01% accuracy in agreement with general relativity. So this gravitational redshift of light was heralded as the beginning of high precision tests of general relativity. Whereas for the deflection of light by the sun, you might have noticed that, it looked like Eddington's estimate was a bit larger, and there was like a 20% error. Then Hipparchus eventually did come up with a high precision estimate, but this gravitational redshift of light was the earlier high precision test. All right, so these first three tests, perihelion precession of Mercury, deflection of light by the sun, and the gravitational redshift of light, these were all originally proposed by Einstein by 1917. Actually, the gravitational redshift of light was first suggested by Einstein in 1907 and 1911 before he even had published general relativity. In contrast, the fourth test that we're considering, one of these four classic solar system tests, was not even suggested until the 1960s, decades later. And it was originally proposed by a physicist named as Erwin Shapiro, and therefore is known as the Shapiro time delay test. So keep in mind that when we have deflection of light by the sun, really the light is sampling different strengths of gravitational potential or different warpages of spacetime. And therefore, there will also be some gravitational time dilation, which simply does not exist in Newtonian theory, right? So the Shapiro time delay is in some ways like a stronger form of this deflection of light test, but it is really its independent test. To put it in Erwin Shapiro's own words, and again, reading this just in case it's helpful for some of you in addition to visually, ideally being able to see this to get an auditory version as well. Because, according to the general theory, the speed of light wave depends on the strength of the gravitational potential along its path. These time delays should therefore be increased by almost 2 times 10 to the minus 4 seconds when the radar pulses pass near the sun. Such a change, equivalent to 60 kilometers in distance, can now be measured over the required path length to within about 5 to 10% with presently obtainable equipment. So in other words, again, we have deflection of light by the sun plus some gravitational time dilation, and it was only a few years later that this was able to be measured. Similar to how the gravitational redshift of light is what I would call a strong test, the Shapiro time delay is, I would say, a stronger test than the deflection of light by the sun alone, because this gravitational time delay is a time delay of general relativity's, you know, light travel time compared to the Newtonian prediction. In other words, one predicts a delay of 0 if Newtonian gravity reigns supreme, whereas this delay has been measured, and it was first measured only 2 years later by MIT's Haystack Observatory, which I visited, well, about half a century later. And so this is me, well, about a decade ago now, as I was just finishing my undergrad and still wearing shorts just about every day. So this is a massive radio observatory. Okay, and then in terms of the Shapiro time delay, again, I've painted a picture with words, but let's go ahead and take a look at a video that I think explains this really quite well. So we're going to, ideally start start this video at the 6 minute and 30 second, roughly speaking. And then let's make sure to speed it up as usual.
Shapiro in the 1960s. The Shapiro time delay is the increase in time it takes for a radar signal to travel past a massive object when compared to if the object wasn't there. Imagine a photon traveling through space. If there's a large mass like a star close to its path of motion, then if general relativity is correct, the mass of the star should distort spacetime around it, which causes the photon to not travel in a straight line, instead following a bent path due to the distorted spacetime around the star. The time taken for this photon to be recorded by an observer then is longer than compared to a photon which seemingly travels the same distance but not near a massive object, and so would take a straight path through spacetime. The star distorts the photon's path, making it take longer than the straight line through spacetime it would have taken if the star wasn't there, as the speed of light does not vary. And any line other than the straight line between 2 points is a longer path, and so it takes longer to arrive for things moving at constant speed. This is the Shapiro time delay. Shapiro himself measured this by bouncing radar signals off of Venus and calculating the change in round-trip travel time compared to when the Earth and Venus were not obstructed by the sun, and then again when the sun was in between. The time delay has also been measured using other planets since then and with distant stars. Other results due to general relativity include the gravitational lensing of light around galaxy clusters, which we know is similar to the bending of starlight around the sun due to its mass, but taken to galactic levels. Another somewhat recent test was performed.
All right, so sweet. So in other words, again, the Shapiro time delay test is not just a solar system test, I should emphasize, but it is also a strong field test. We can consider it around black holes as well, in regions of really extreme gravity. Now, one thing I want to point out is that all 4 of these classic solar system tests use the Schwarzschild metric, at least within the solar system. And that's okay because things aren't really spinning very much in the solar system. I mean, they are, obviously, we're moving around the sun, but what I mean is that the motions, the rotational motions in the solar system, are very, very slow compared to the speed of light. Whereas for the Kerr metric, for that spin, it only really has a huge effect when that spin is close to the speed of light. So for modern tests, the first one we'll consider is actually using a different metric. That's so-called lens Thirring precession, maybe familiar to you all now, since we've talked about Mercury's perihelion precession. But lens Thirring precession is really a kind of different beast, and this is due to so-called frame dragging, or in other words, due to the drag that an object feels as it traverses space-time, basically moving at a different rate than space-time itself is being spun in case of extreme gravity or extreme spin. And this is an effect that comes from the Kerr metric, and it wasn't predicted for a pretty long time. But it was first measured by Gravity Probe B in 2011. Gravity Probe B actually went up in 2004 for initially planned, I think, 3 or 5 year mission, and they had to get it extended before they could finally get a measurement. I'm very thankful that they did get that extension granted so that they were able to come up with a full measurement. And just remember that, okay, this gravity probe A was several decades earlier, which was measuring that gravitational redshift of light. So in terms of understanding this, you can see I've had a couple of videos here from David Butler. I really love these classroom-made videos. They're really fantastic. So let's take a quick look at what frame dragging is in general relativity now. All right, let's go.
In order to understand what is going on in and around a black hole, we need to cover the twisting effect of rotating masses on the space surrounding them. The name given to the twisting is frame dragging. The space is literally dragged along with the rotating mass. The effect was derived in 1918 by physicists Joseph Lenz and Hans Thirring. It is known as the Lenz-Thirring effect. They predicted that the rotation of a massive object would distort the space-time metric, making the orbit of a nearby test particle precess, like a gyroscope. This does not happen with Newtonian gravity, where the gravitational field of a body depends only on its mass, not on its rotation. It wasn't until 1963 that a mathematician named Roy Kerr discovered a significantly more complicated metric for rotating bodies that made it possible to calculate the precession one can expect from a given mass and rotation of an object, like the Earth.
Right. So keep in mind that even though Lenz and Thirring pointed out that there should be this effect, like way back in 1918, that was just a statement. It wasn't until Kerr came up with this metric in the 1960s or 70s that there, and I think it was Kerr himself who was able to come up with the estimate of the effect as well.
To test this effect, NASA developed a satellite called Gravity Probe B and put it into orbit 264 kilometers above the Earth in 2004, where it operated for a year. It used a set of super-sensitive gyroscopes to measure precession due to frame dragging. It also included a non-gravitational drag identification gyro and compensation microthrusters to maintain a non-gravitational drag-free environment. It compensated for solar radiation drag and atmospheric disturbances drag. By 2011, data analysis had confirmed that frame dragging did occur and measured it to within 15% of the amount predicted by the Kerr metric for Einstein's field equations.
So again, this was quite a difficult test in terms of all those different effects that can modify it. Look at this frame dragging precession. It says the number of degrees per year. So of course, if this was represented in arc seconds, it'd maybe be a little bit more feasible. But it's really a tiny effect. That's part of the challenge in terms of going beyond general relativity. So we need really high precision metrics or tests of stronger gravitational regimes. So speaking of stronger gravitational regimes, let's dig into the Hulse-Taylor pulsar. And I'd like to go back to slideshow mode if I can. There we go. So in terms of this pulsar, what is a pulsar? Well, it's kind of like a celestial lighthouse that a pulsar basically pulses. So these pulsars were first discovered by Jocelyn Bell Burnell in 1967, and only a few years later, in 1974, these pulsars the discovery of them were granted the Nobel Prize in Physics. And then Jocelyn Bell Burnell was not amongst the awardees, and this has led to really a lot of discussions historically about equity in astronomy, and arguably Jocelyn Bell Burnell should have been part of one of the awardees here. So this is quite unfair and is subject to a lot of discussion. So if you're interested in that sort of thing, there are occasionally the Society for Women in Physics. You maybe have had a rename, but I think that it's still called the Society for Women, maybe Plus in Physics. Have a annual meeting, although I think it's every 2 to 4 or 5 years. So they have a meeting, and it's a really great time if you're interested in physics. I'd highly encourage you to check it out. I've never been myself, admittedly, but I've heard that it's a really great time, and it's a fully paid for trip if you get your application accepted, I guess I should say. But the physics department has sent students to CUWIP, I should say, the Conference for Undergraduate Women in Physics, which is maybe related to, in Michigan, we had a Society for Women in Physics, but the Conference for Undergraduate Women in Physics is, I think, independent of that. Okay, so anyway, moving on to pulsars in this Hulse-Taylor binary pulsar. Okay, what does a pulsar look like? We have a very nice and brief animation here. So we don't really need all this red material around it, but the main thing is that while a pulsar pulses. Or in other words, we have a very compact object that's known as a neutron star. So it's much, much smaller than a white dwarf. You learn much more about these objects in Astro 105 Stars and Galaxies. But basically, we have a compact object that has some X-ray and radio emission that is really emitted in its polar regions. And if one of those polar regions is kind of lined up with Earth's motion or with Earth's orbit, then we see when that overlap occurs. And these spin very, very rapidly, such that some pulsars occur with millisecond cadences, some with second-long cadences. And now this is actually a binary pulsar. For the Hulse-Taylor pulsar itself, only one of them is a pulsar, and the other one is still a neutron star that we infer indirectly. But it was not a double pulsar. And we have discovered double pulsars, which are actually much easier to work with. But so this was detected in 1974. It didn't win the Nobel Prize for quite a little bit, not until 1993. And partly that's because it wasn't used to test general relativity really conclusively until, say, 2010 or so with this Duisberg paper, although already by the 1990s, there was really a significant effect found. So one would expect this line of zero orbital decay for Newtonian gravity, whereas general relativity predicts that as two objects in a strong regime that are rotating in such a way where there's a quadrupolar moment, that there should be the emission of so-called gravitational waves that sap energy from the system, and therefore the periastron, in other words, the closest approach between these two objects, should shrink with time. And in fact, the periastron occurs sooner and sooner and sooner. And for these two particular objects, they're projected to collide in an astrophysical medium amount of time, about 300 million years. So it's still quite a long time. All right, and then I just talked about gravitational waves, but let's take a look at classroom aid starting at 1 minute and 11 seconds in this video. And this time maybe I won't even go 2 times speed since it's pretty short.
This one was pulsing every 59 milliseconds.
He talks a little bit slow. I have a need for speed, so let's go a little faster.
Indicating that the pulsar rotates 17 times per second. But Hulse and Taylor noticed that the pulsars varied regularly every 7 3/4 hours, with pulses arriving 3 seconds earlier at some times relative to others. This meant that the pulsar was in an elliptical orbit with another neutron star. This was the first binary neutron star ever discovered. Using the orbital motion, they calculated the star's masses, their closest approach, called a peristron, and their furthest distance apart, called the apastron, as well as the system's inclination. With this information and the gravitational wave equations, they were able to calculate the amount of gravitational radiation, the expected decay of the orbit due to the lost gravitational energy, and the corresponding reduction in the time it takes per orbit. This graph maps the accumulated reduction in orbital periods against time, assuming that Einstein's equations are correct. Hulse, Taylor, and others have studied this binary system for 40 years now. This graph records their measurements. We see that the measurements fit the theory perfectly.
All right, so very cool. And it does make me wonder, okay, so time till merge is 300 million years. I sure hope we don't have to wait 300 million years until we have some better theory of gravity. But it took 150 years to find Mercury's anomalous perihelion precession. It might take many more decades, perhaps, until we have uh, some sort of deviation between what's expected from Einstein's theory of general relativity and the measurements. So only time will tell. Although beyond the Hulse-Taylor pulsar, maybe we have to wait a few more decades there. Maybe we have to wait many more decades or like a century or 2 centuries there. We thankfully do have even stronger tests of general relativity now. And this is so the Hulse-Taylor binary pulsar was indirect evidence for gravitational waves. We now have direct evidence for gravitational waves. These were first conclusively measured in 2016 by the Laser Interferometer Gravitational Wave Observatory, or LIGO. This was, there was absolutely fanfare in the physics departments, in the streets, so to say. when this was discovered. I was visiting a colleague at the University of Madison, Wisconsin, and it was an absolutely amazing time to be alive and to be in physics. And really, every year is getting a little bit better in terms of gravitational waves. Um, Now, we've talked about Nobel Prizes several times in this class. Again, this detection was in 2016. It won the Nobel Prize in 2017, 1 year later. That's just how big of a deal this was, the rapidness of the Nobel Prize. Now, remember Kip Thorne from that MTW book? A few fun facts about Kip Thorne. First of all, Kip Thorne was the science advisor for the movie Interstellar. If you haven't watched the movie Interstellar, I think it's good up until they go into the black hole. But it's very, very good overall and talk about like love being the fourth dimension, blah, blah, blah. But Kip Thorne was the science advisor for Interstellar, which came out, in fact, before LIGO made its conclusive detection. Um, and then Kip Thorne was visiting Michigan. I decided to not include my embarrassing photo this time since Kip Thorne does not look super with it in the background. But again, so Kip Thorne was one of the three authors in MTW. Kip Thorne was the PhD student of John Archibald Wheeler. Now, regarding gravitational waves, we have from the LIGO lab itself at Caltech, as well as MIT, this journey of a gravitational wave. So let's take a look at this.
This is the sound.
All right, so as the person is about to say, but I will beat them to the punchline. The sound that you're hearing is a sonification of the frequency of the gravitational waves uh, that were received by LIGO. They're not something that would really be audible per se, but nevertheless, you can make a sonification of the signal.
Sound of two black holes colliding and merging. Where did this sound come from? A long time ago in the...
And then I want to speed this up a little bit. It's not a very long video, but we have a lot of material to cover today, although we're getting towards the end. Phew.
Distant reaches of the universe, two black holes, each about 30 times as massive as our sun, were locked in orbit and spiraling in towards each other. The only visible traces of this...
All right, one other thing I'll mention, although you'd learn potentially more about this in Stars and Galaxies, is that these 30 solar mass black holes, and LIGO has discovered mergers of like 20, 30, 40, 50, 70, etc. solar mass black holes. We weren't expecting those to exist, actually. People thought originally that all black holes had masses of something like less than 10 solar masses or more than thousands of solar masses due to so-called pair instability supernovae, whereas evidently there's something weird going on that we're still trying to figure out here to some extent.
Cataclysm would have been the way their gravitational fields warped the light of distant stars. Even as they collided and merged, there wasn't a flicker of light to be seen. The real and very violent action in the system was in the form of gravitational waves, ripples in the very fabric of space and time. These waves were constantly draining energy from the black hole orbits, leading to their ultimate collision and merger to form a single black hole. At that instant, the power of the gravitational waves was 50 times greater than that of all the stars in the universe combined. That pulse of gravitational waves, lasting only a fraction of a second, expanded through the universe, passing unimpeded through countless galaxies. About 1.3 billion years later, it reached Earth. Gravitational waves alternately stretch and squeeze space itself and everything they pass through, but the effect is minuscule. Their effect on Earth here has been vastly exaggerated to help visualize something that is otherwise invisible on this scale. To detect them and directly measure their properties, scientists built LIGO, the most sensitive measuring device ever made. LIGO uses a device known as an interferometer to measure the tiny displacements in space. In the simplified representation, a laser beam is sent towards a partially reflecting mirror and split along two paths. The beams travel along 4-kilometer arms and reflect back towards the central mirror, which recombines them, directing their light to a detector. As the gravitational waves pass, the distance between the central beam splitter and the end mirror stretches along one arm and compresses along the other. This changes the time it takes the light to travel along the arms. The recombined light waves shift with respect to one another and produce a signal at the detector. Incredibly tiny stretching and squeezing of space can actually be measured directly in this way.
All right, so the key thing here is notice that when the arms are not being deflected, we had this case where there's no red light actually going to the detector. That is because these two waves are in perfect destructive interference. Notice that the crest of each wave lines up with the trough of the other one. So that's why they were able to measure such a sensitive signal, as they're about to discuss actually, is because it makes it a little bit easy to interpret. Most of the time, you get nothing at the detector. It's only when there's a gravitational wave affecting the distances that you end up with some signal at the detector. And I should mention that although this was discovered in 2016, is a result of decades of work that led up to it. I think it was 1998 or so that one of the first gravitational wave observatories was built or was worked on. And really, you need absolutely minimal noise. There was a lot of work investigating doing this, like under mountains, to reduce vibrations and random noise. And ultimately, for LIGO, they chose to simply build a large enough facility that it would the signal could dominate over the noise.
Between the central beam splitter and the end mirror stretches along one arm and compresses along the other. This changes the time it takes the light to travel along the arms. The recombined light waves shift with respect to one another and produce a signal at the detector. Incredibly tiny stretching and squeezing of space can actually be measured directly in this way. How little does space distort to make this signal? Let's zoom into a hydrogen atom until we reach the proton at its core. LIGO is so sensitive it can measure changes in distance as tiny as 1,000th the diameter of a proton. And this tiny measurement, made by LIGO, was the final step in a journey that began 1.3 billion years ago in the distant universe when two black holes collided.
All right. Again, absolutely fantastic. And then again, this absolutely minuscule signal, right? 1/1000th of a proton's size. Okay. So let's go on. So today, 2026, this is coming from Wikipedia, but we have over 300 detections. There's been a lot of great work done by LIGO and beyond. In fact, generally the bigger baseline, or in other words, the bigger separation between the measuring arms or devices, the more sensitive measurements we can make, and also the longer wavelength gravitational waves we can observe. And then also, the more observatories we have, the better we can localize where the signal came from and start to understand with X-ray or radio, et cetera, follow-up what astrophysically, uh, what other astrophysical signals might identify gravitational waves. Um, so Virgo, the European equivalent of LIGO, was really operating about the same timescale as LIGO, and a combination of the two first found gravitational waves from merging neutron stars in 2017, 1 year after LIGO first found gravitational waves from merging black black holes. And these are really important in terms of understanding the neutron star equation of state, which might change our fundamental theories of particle physics. Neutron stars are in some ways like gigantic, like city scale nuclei or atomic nuclei. So they might help us better understand the strong nuclear force or particles beyond the standard model of particle physics, which we won't really talk about until much, much later. All right, and then Kagra, which is the Kamiokande or Japanese kind of version of LIGO, or really that's maybe unfair. It is a great gravitational wave observatory in its own right. Just came online a bit later in 2020. And then we hopefully will have LIGO India coming online in 2030 plus or so. Unfortunately, so you saw in that video that there were really two observatories that were instrumental in detecting that first gravitational wave. There was LIGO Hanford and LIGO Livingston in Louisiana. LIGO Hanford is slated to be cut this year. I mean, hopefully it survives, but and I don't really want to get into politics. I guess on the plus side, we do have our European and Japanese systems, although it'd be great if the US could lead the charge here, I would say. Okay, moving on to tests of general relativity. Um, uh, Really, the last one would be gravitational lensing, but I've decided that we will skip that again. Okay, so we're now done with that segment on the tests of general relativity. We're getting towards the end, and you probably noticed that this last segment is a little bit more rushed or a little bit less detailed than the preceding sections. So I would recommend pausing the video nevertheless and taking a bit of a break. Okay, so unpause. My goal, I should have mentioned at the start, is for you all to spend about 2.5 hours on this lecture. I unfortunately don't have any worksheets for you all to work on today. And in terms of that 2.5 hours, I expect part of that time is jotting down notes, etc. So it's not just about watching the video for its duration, but also working on your notes, the attention checks, etc. Okay, for the cosmological principle, our goals for learning for this segment, which extends a bit beyond the cosmological principle, admittedly. First, kind of definitionally, just like we started this class with what is a metric, we'll be sort of ending this class with what is the cosmological principle. Then we'll go into why Einstein ended up fudging his field equations, and then much later we'll maybe understand why this was ultimately a good thing. And then third, we'll talk about the observations for an expanding universe and why these were used to drop the cosmological constant, although very briefly, admittedly. Okay, so getting into this cosmological principle, this is ultimately an extension of the Copernican principle, or and this cosmological principle is really a foundational assumption that underlies modern cosmology. So keep in mind that if there is evidence that overturns the cosmological principle, then we are SOL, or we are really out of luck, supremely out of luck, I'll say, regarding understanding the universe. So again, the Copernican principle says that the Earth does not specify a special position in the universe. Or in other words, the Earth goes around the sun. Put this a different way, though, it means that when we do experiments on Earth, we would expect the exact same laws of physics to apply anywhere else in the solar system or anywhere else in the universe. So if we understand, very high precision tests of the law of gravity on Earth or around the orbit of the Earth, we expect those laws of physics to apply just as well on the moon or in other places. Maybe the parameters are different, right? The mass of the moon is different than the mass of the Earth, but the same fundamental physics we still expect applies. And nevertheless, that is an assumption. Now, so the cosmological principle, again, my framing of it is that the laws of physics are the same everywhere. And a kind of consequence of this is, speaking in terms of the universe as a whole, that we then require isotropy as well as homogeneity. So, to put this in a simpler way than these fancy words, really nice quote by Andrew Little, his textbook from 2003. The cosmological principle means that the universe looks the same whoever and wherever you are. So it's almost like a, cosmological democratic principle, if you will. Okay, and then in terms of better understanding like this isotropy and homogeneity, though, although I think this video more touches on isotropy, which is fair enough. Let's take a look. And again, I want to speed this up, save us a little bit of time.
When we look out into the universe far enough, we see on average the same distribution of galaxies in all directions. In other words, there is no preferred direction in space. It's isotropic. But being isotropic for us doesn't necessarily mean it is isotropic for viewers in far-off locations. It is possible to imagine galaxy configurations where things look the same in all directions from one point of view and not from another. But this is unlikely.
Okay, so again, so isotropy means everything looks the same at different angles. Homogeneity means that space itself is the same. So in order to have isotropy from all positions in space, that would require homogeneity.
Our assumption is that all observers will see the same isotropic distribution of galaxies. In other words, there is no preferred location in the universe. It's homogeneous. Galaxy densities are the same everywhere, as long as we are viewing large enough distances and volumes. This is the cosmological principle. It simply states that the universe is both isotropic with no preferred direction and homogeneous with no preferred place. All directions are equal, and all places are equal as far as the laws of physics are concerned.
All right. So I think that put it very, very well. And so now moving beyond the cosmological principle, let's move on to cosmology. So in terms of cosmology, let's talk about why Einstein fudged his field equations with so-called cosmological constant. And the background from this you probably have read in the book already. Einstein thought that a static universe was really the only philosophically acceptable position, and this really fit in line with what all the major physicists at that time believed, that the universe had to have been eternal. And And in terms of Einstein's original field equations, it seemed like impossible for this to be the case if there was only a gravitational force, right? Either everything in the universe is arranged in just the right way perfectly, where the universe is really static, or if there's any slight displacement, where there's some slight overdensity, then gravity will end up causing the entire universe to collapse down to a point. And that seemed untenable because, well, the Earth moves around the sun, or vice versa in the Galilean relativity format. So, in other words, there is motion, so there has to be some sort of force, so to speak, counterbalancing gravity. And so, for this anti-gravity force, Einstein ended up choosing a constant term, which he called a cosmic fudge factor. And so this is this additional term in the Einstein field equation. This lambda is a constant, similar to how kappa, Einstein gravitational constant, is, well, a constant. And then the cosmological constant is being multiplied by the metric. And we have, again, learned about some of the different metrics that can be applied in general relativity, although the metric tensor can be a little bit more general. Okay, so in terms of abandoning the cosmological constant, doing this admittedly like much more briefly, but you all read about this in much more detail in the book, ideally by now. So Friedman in 1922 or so first found that there could be some non-static solutions to Einstein's original field equations, and Einstein really berated Friedman about this, about how it was absolutely pointless to consider non-static solutions, and how ridiculous Alexander Friedman's work was. Um, Lemaitre observed the universe expanding in the 1920s, along with Schleifer, but Lemaitre was one of the folks that really published this the most. But people largely ignored him, possibly because he was a priest, and this was considered still quite unfashionable, right? So it's very hard for scientific revolutions to happen until there's, we'll say, sufficient evidence. So just in summary, Friedman and Lemaitre together showed, one theoretically, one more observationally, that the universe is expanding in the 1920s. But really, Hubble was the one that came up with really conclusive evidence that unless the universe was expanding, the cosmological principle would be violated. So it was because of the cosmological principle that Einstein really clung to more fervently than a static universe, that Einstein caved and eventually, I believe, apologized to Friedman. So keep in mind that if the universe is expanding, then we have implied an origin of the universe in time. And that means that, of course, the universe is not static, and therefore we don't need necessarily a force to counterbalance gravity. Just like if you throw an object up, it'll come back down. So the universe, if it had a beginning, it could have an end. Or if you throw an object up hard enough, it'll, escape the Earth's atmosphere and coast further. That was also thought as one possible outcome, that maybe the universe was coasting. All right. And as a result of this realization that the universe is in fact expanding, Einstein called the cosmological constant the biggest blunder in his life. There's been some debate about whether Einstein actually said this. This was first kind of reported in George Gamov's book, who we'll learn about later, and I think not like until 1993 or so. But there were other scientists who, aside from George Gamow, who have reported similar statements by Einstein. And I think it's fair to say that Einstein didn't really roll with the cosmological constant after the 1930s. All right, and now regarding the great debate in Pickering's Theorem, which you all should have read about over this past week, that is admittedly going to have to wait until the next episode. So this is really fun, historically speaking. So hope you have a great time. Again, apologies for this video being so late. but I hope you all enjoy it almost as much as I did in putting it together for you all. All right, so ciao.